go ahead and see if this pre-processed image will work with the find gates function. So let's go back to the code section where we have find gates, and here I pick contrast adjusted image in the drop down menu, and this should go ahead and run the section, and here is the output for the detection result. As you can see, it has successfully worked with this image as both gate structures have been annotated, and this is the desired result from our gate detection algorithm. So what we are seeing here is that we were able to explore and try different pre-processing techniques in MATLAB without knowing a whole lot about these techniques before using contrast adjustment to successfully pre-process this image and make it work with the find gates function. Now note that we had to do some amount of manual tweaking of color channel levels in IMadjust to get the desired result. And this was just for one image. Now imagine if we had a large sequence of say 500 to 1000 images or frames in a video containing the gate structure, changing lighting and underwater conditions. Here it will be very hard to expect the same pre-processing technique and settings to work successfully in detecting the gate structures across all these images. In this case, it will be required to run and verify the pre-processing steps across all the images, and then possibly go back and tune the pre-processing algorithm and also the find gates function and make them robust enough to work across all these images. Image batch processing app makes this whole workflow very quick and easy within MATLAB. Let's go ahead and look at this app and use it for automating the pre-processing of a sequence of images of the underwater scene. To open this app, let's go to the Apps tab and click to expand the drop-down list. Here, look for Image Batch Processor app under the Image Processing and Computer Vision section. Notice that there are many other apps that are available under this section. Apps are a great way to get started with exploring and trying different techniques or algorithms, especially if you are new to image processing or computer vision. Let's open the Image Batch Processor app for now. Now, I would like to read the sequence of images of the underwater scene that I have and then apply the same contrast adjustment algorithm to pre-process all these images. To do that, I'm going to load my image set. You can see all the loaded images as thumbnails in the left panel here. And here is a preview of the selected image. Next, I'm going to select the algorithm that I want to use on these images. I have my script containing the contrast adjustment part saved as a new function. It's called preprocessimage.m. If you wish to learn more in detail about the steps to create this function, please click on the question mark button to refer to the documentation. Next, I'm going to select Process All to run the function on all the images. Once it is done executing, you can view the results in the right panel here. You can expand and inspect them further. Also note that the app allows accelerating batch processing with parallel computing. This is specifically useful when you want to accelerate working with a very large image data set. You can then export these results to MATLAB for testing with the find gates function, and this as well could be automated in a script. So it is important to note here that the Image Batch Processor app enables us to easily automate processing large sets of images and then use these results to go back and fine-tune our algorithm to make it work across all the images. As we have seen, processing multiple images is easy and can be accelerated using the Batch Processor app. Please also note that MATLAB now provides an image data store object that makes it easy to access and manage large collection of images. Now what we have seen in our demo were just a couple of simple enhancement techniques, but there are many other techniques available in MATLAB to use depending on our problem. For example, deblurring, which is very useful when you're trying to remove blurring from your images, or image filtering techniques to remove noise in images. You can learn more about filtering and enhancement techniques by referring to the link in the description below. That brings us to the end of this demo. In summary, we saw how easy it is to get started with MATLAB using the help documentation, which provides you with a very good set of ready-to-use examples and comprehensive function reference pages. We saw that MATLAB live scripts are interactive and make it easy to explore and iterate on different techniques and their parameters and to view intermediate results. We also saw MATLAB provides you with an image batch processor app through the image processing toolbox that lets you automate testing your algorithm with large sets of images. In the previous demo, we saw how to enhance images. Now let's look at the next demo on how to process images to extract useful information from them. One of the primary goals of cameras on robots or UAVs is to detect objects in front of them, especially in robots that are performing tasks like pick and place, obstacle avoidance, or target detection. Here is a simple example of a pick and place robot in the image on the right, whose goal is to move towards specific colored cones, pick them up and move them to a bin. On the left is an image of what the robot sees from its front-facing camera. Now, this might seem an easy task to find the cones to our naked eye, but not necessarily for the robot. So why could this be a challenge? If you notice, there are other objects around the target objects, that is, the cones. Also, the position, orientation, and scale of the cones make it hard to find them. This is a common challenge in object detection problems, like when designing traffic monitoring systems or vehicle or pedestrian detectors for self-driving cars or pick-and-place robots in warehouses. So the main objective here is to separate or segment out the regions of interest from the rest of the clutter in the image before detecting their actual position in the scene. Image segmentation will help us solve this problem. Segmentation techniques enable extracting meaningful information from an image by assigning all the pixels in a region with similar properties the same value. This is called masking. For example, a binary mask would involve assigning all the pixels in an image either a black or a white value. This way, we can separate out the right screens in the foreground from the background. Now you can analyze this binary image further to say, for instance, count the number of grains in the image. Now image segmentation techniques are used in a variety of different applications, like in optical character recognition, where sometimes the text in the image needs to be first extracted before actually recognizing them. In visual inspection, where you are segmenting the image based on intensity before finding the defective object. Or in medical imaging, where you perform color-based segmentation on tissue images to extract the regions of interest for further analysis. For our problem, you might wonder, how do we know which technique to use? Well, like in the first demo, by doing a simple search in MATLAB help on segmentation and looking through some examples, I was able to quickly figure out that color thresholding would work well in our case. Color thresholding will enable separating out the individual colored cones and then use the results to detect the exact location of the cones in the image. Now let's go to MATLAB and see how to perform color thresholding. So how do I get started with color thresholding in MATLAB? For this, I'm going to first navigate to the help browser, and here I'll search color thresholding. And here are my search results for color thresholding. The first result here says color thresholder. Let me go ahead and click on this. And here I can see that there is a color thresholder app that I can actually use to perform color thresholding in MATLAB. I also see that there is an example that I can open up and learn more about how the app works. Now let me go back to MATLAB and open up color thresholder app. Like what we did before, I'll go to the apps tab and scroll down to the image processing and computer vision section, and here I can look for the color thresholder app, which is right here. So this is our color thresholder app. Next, I'm going to import my image that I'm going to be working with. To do that, I'll click on load image and select load image from file. Here are my image options. I'm going to select the first one, which is cones1.jpg. So the app now loads the image and displays it along with different color spaces with point clouds representing the image in each of these 4 color spaces. And these color spaces are RGB, HSV, YCB, CR, and LAB. Here I can select the color space that provides the best color separation for my image. I can learn more about these different color spaces and how to work with them from MATLAB help documentation. For now, I'm going to go ahead and pick the HSV color space by clicking on the HSV button here. So this should open up a new tab called HSV and display the image. You can also see on the right here we have some interactive controls. These controls let you adjust the three values that represent this color space. H is a pinwheel with all the hue values, which basically represent the different dimensions of color. S is nothing but the saturation values, which represent the darkness or lightness of that color. And V is the intensity value of the color in each pixel in the image. You can also see that there is a 3D point control at the bottom. Now, I will go ahead and interact with the three HSV controls on the top to adjust these values. As I change these values, you can see that the image on the left is updated in live by filtering out the pixels based on the HSV values that I select. I could also use the point cloud control to perform similar filtering operations. Let's go ahead and select all the hue colors that match yellow and shades of yellow. So what we see now, based on our filtering operation on the left, is a masked image which contains only the pixels that match the HSV value selected. I can move the pinwheel value around to select a different color. Say let's choose red and shades of red. And now you can see it actually filters all the colors except for red and shades of red. I can then fine-tune my mask by adjusting the saturation and intensity values. Next, you can also try color thresholding in a different color space by selecting New Color Space to start a new session. This way, you could explore thresholding in different color spaces and pick the most suitable result for further analysis. In MATLAB, I could have performed color thresholding programmatically as well, but as you can see, the Color Thresholder app makes this workflow much more interactive and easier to explore the different options. We could get a decent result really quickly without knowing a whole lot about the color spaces and the values representing them. Now that I'm happy with my results, I can go ahead and export the masked image to MATLAB Workspace. I can do that by going to the Export option and clicking on Export Images. As you can see, I can also choose to export the binary mask and the original input RGB image. This way, I can use those results to further analyze and detect the cones in the image using a few other techniques. Now, what if I wanted to apply these steps to a large set of images? To do this, I can use again the Export option and click on Export Function. This way, I can export the Color Thresholder app session as a MATLAB function. And now, I can use this function in future to programmatically threshold more images with the same algorithm and same settings. So let's go ahead and look at this function that got created. It's called create mask, which takes in an RGB input image and gives out a binary mask and a masked RGB image as the output, very similar to the Color Thresholder app. Let's go ahead and save this function to our current folder with the name create mask. Now I have a live script here that I've created that uses this function and a few other analysis and detection techniques to detect the cones in the image. So let's go ahead and take a look at the script. In the first section here, I read a new input image, which is cones4.jpg. The second line here is the create mask function. Let's go ahead and run this section. So here is the output, the three images. The first is the input image, then the masked RGB image, and then the binary image. In the next section here, I'm going to use a segmentation technique called morphology to further refine the binary mask. In this case, I'm going to filter out smaller pixel regions in the image. And the way I do that is using the IamOpen function. And then I use the bwconComp function to find all the connected components in the image. Let's go ahead and run this section. And here is the output of the IamOpen function. As you can see that the binary mask has been further refined. Finally, in this section, I'm going to use the region props command to find the position of these connected components, which are the cones in this image, and then annotate the original image with the information that I have from the region props, which is the position of these connected components. So let's go ahead and run this section. And here is my final result, which is the original image that has been annotated with the position of the red cones in this image. So this way, I can perform this operation on multiple input images and use the information to go back and fine-tune my thresholding values and the detection algorithm. Now, color thresholding is just one of the many segmentation techniques available that you could consider for solving your problem. MATLAB actually provides you with a comprehensive list of many other segmentation and analysis techniques. There are also functions to perform object and region property analysis, similar to what we did with detecting the cones using the region props command. You'll also find that there are numerous well-explained examples that show you how to use these different segmentation and analysis techniques based on real-world problems. So, we saw there are many other segmentation techniques available in MATLAB as ready-to-use functions. MATLAB also provides an app through the image processing toolbox to make segmentation fast and interactive. You can explore different techniques on your image and refine your results until you get your desired results. You can export these results to MATLAB for further analysis. You can even choose to generate MATLAB function for your session and use them to automate testing the same algorithms on a large set of images. This is especially helpful if you're applying segmentation to sequential frames in a video. So, in summary, in this demo, we have seen how color thresholding app was very effective in quickly exploring the different color spaces and then tuning the values to get the desired segmentation results. We saw that MATLAB provides with a variety of segmentation algorithms to use in our work, with solid documentation and examples to get started with applying them quickly. We also learned that Image Segmenter app is available through the image processing toolbox that enables exploring and trying out some of the segmentation techniques interactively on our images. So that brings us to the end of this talk. In summary, we have seen how image processing can be made easy to get started with using MATLAB. We specifically saw through the demos that MATLAB's comprehensive help documentation makes it easy and quick to get started with discovery and learning. The ready-to-use examples provide a quick starting point to try out different algorithms with your own data. Interactive apps and live scripts make it convenient and fast to explore and iterate on different techniques and their parameters before deciding which ones work best in your case. Finally, testing an algorithm on a large data set of images or a sequence of images is so much easier in MATLAB. So where do you go from here? Well, here are some next steps. Image Processing Toolbox can do more than what we covered in this video. To learn more about this toolbox, go to the product page on mathworks.com. If you're ready to explore and evaluate the image processing toolbox, get a trial license of the product today. You can also get a more detailed and hands-on experience with the toolbox by signing up for an image processing with MATLAB training course. This is also available as an online course. If you're interested in solving computer vision problems specifically, then MATLAB's computer vision toolbox can help you with that. Many of our customers are interested in using deep learning techniques in their vision-based applications. If you didn't know already, we have a deep learning toolbox that can enable you with using deep learning in MATLAB. Please refer to the description below for links to these resources. Thank you for your attention.